So today in the physics lab, we are looking at this wireless smart cart here that we have on the track. And I've got this smart cart connected to two springs, one on either side. And I'm going to pull up the smart cart here. It's already been connected. And I'm going to do a position versus time graph. And we're going to take a look at what it looks like here. So I'm going to hit the start button to start recording some data. And I'm going to displace the cart over here a little bit. And I'm going to let it go. So I think this is pretty much expected. It's going to oscillate back and forth, and both springs are going to pull it and push. So let's take a look at this data a little bit closer. Stop that for now. And what you can see here is you can see that I started recording it. It wasn't moving. Then I moved it over to my initial start position here, and then it kind of oscillates back and forth. So this demonstrates simple harmonic motion. So simple harmonic motion is where you have a restoring force that's bringing the system back into balance. So looking at this thing right here, this is the equilibrium point. This is the center point. This is where the cart wants to be. And since I started it with the cart sitting here, it thinks 0 is my equilibrium point. Okay, great. Then we can see that it has a maximum here where it started, and then each time it oscillates, it tries to get back to that maximum. It doesn't quite get there. If we pull up points here, if I click on this point, let's go back over here. Okay. So here you can see the maximum, it says, is 0.0686, whereas if I look here at this maximum, or minimum down here, it goes a little bit further, so 0.07, and then this one is a little bit further 0.0728. And so what's happening is that's the maximum, that's the amplitude. So the amplitude is going to be how far it goes from the equilibrium point up or the equilibrium point down. Now this is simple harmonic motion, but there's another thing on top of it called damping. Damping, you can see it's causing the curve here to get smaller and smaller. So you can imagine there is a point, let's get rid of this so you can see what I'm talking about. If you look here, you can imagine that there's like some sort of curve bounding the upper and lower portions of this, and that's due to friction between the wheels and the track. It's just losing some energy that way. In this class, we're not going to look at damping too much, but I want you guys to realize that in real life there is friction, there is damping, and it is going to slow it down. But we're not going to pay too much attention to that. But when it comes to amplitude, looking at real life data, the amplitude decreases because amplitude represents how much energy is in the system, and since we're losing energy to friction, well, the amplitude's going to decrease. Okay, so that should be pretty easy there. Now, the other couple of things I want to look at here are the time period or the frequency. So frequency is the number of cycles per second, and time period is simply how long it takes one cycle to occur. And they're inverses of each other. So when we're looking at this data here, it's actually going to be a lot easier to find time period, because time period is simply from where you start to where you end. So if I take this data point here, and let's say go up to this point right here, where we're at a maximum. Oh, too far. Go to this point where we're at a maximum, and I hit this little delta tool. I need this tool to be, let's go to just the next data point here. So it's one full cycle. So I'm going from, in this case, a crest to the crest of the next wave. And here it's giving me a delta y, which would be my, delta y would be my amplitude. That's how much energy we lost. Delta x is my time. So here it's giving me a time period of about 1.2 seconds. If I want to make sure my time period's accurate, I should actually get as many of these time periods as possible. So here, if I went here, let's see how many cycles. So we got 1, 2, 3, 4, 5, 6, 7. So that would be 7 cycles. I'm going to grab a calculator here. And if we're looking at the 7 cycles, it says that the time period for all 7 cycles is right there, your delta x, the 8.25, okay? So we take 8.25 and divide by the 7 cycles, I get 1.178, so about 1.18 for the time period, which isn't exactly what I had before, because it's going to be much more accurate to get multiple cycles and average them. But it was close. We had basically 1.12, I think, or something. So very close in terms of hundredths of a second. But ideally, if you want to find time period, you measure several and then divide by how many time periods you have, like we've done here. So if your time period is 1.18, and you take that and you do the inverse of it, so do 1 over that number, we can get our frequency. And so the frequency here is 0.84, or about 0.85. So the time period means how many cycles, how long it takes for one cycle. So in this case, it's a little over a second for one of these cycles on this setup that we have here. Frequency is how many cycles per second. Well, if it takes a little bit longer than a second for a full cycle, well, that means you're not going to get a whole wave or a whole oscillation in that second. And that's what we see here with the frequency, that it's only 0.85. So we're only getting about 85% of a full cycle in 1 second. Okay? So that's kind of time period and frequency for you.